Hello, everyone. My name is Christel Michielsen, and I'm working at the Jülich Supercomputing Center. There, I'm leading the group Quantum Information Processing, and I'm also the head of a quantum computer user facility called UNIQ. So I'm going to tell you something about quantum annealing for optimization and classification. So as you all know, quantum computing is a new disruptive compute technology. And there is a diverse user group of science and industry who has various hard computational challenges to unravel complex systems. The potential applications for quantum computing are quantum simulations, optimization, and as optimization is also part of machine learning, also quantum machine learning is another potential application. Now, there exists a large variety of quantum computing devices. On the bottom left, you see various of these devices built from superconducting qubits. We have them from semiconductor qubits, trapped ions, neutral atoms, spin qubits, and so on. So in order to somehow classify them, we came up with the quantum technology readiness level scheme, which describes the maturity of the quantum computing technology. Now, on this scheme, we have 9 levels ranging from 1 to 9, and we have indicated, and it's somehow subjective, where one finds the experimental multi-qubit systems, which one is developing in university and research center labs. They all have a level of 2 or 3. The reason is the systems are small and the qubits are of less quality than what the bigger companies can develop. So the ones of IBM, Google, and Rigetti computing, quantum computing, for example, but also the ones of IonQ and other companies, they have a level of 4 or 5. These systems are bigger and the qubits have a higher quality. Then, because we wanted to use the same scheme for the classification, we also have entered there the D-Wave quantum annealer, although this is a different type of quantum computer. And we have given the D-Wave quantum annealer a level of 8. The reason is that these are scalable systems and that they are in the meantime large enough to perform some tests which go in the direction of prototype applications and use cases. But it's clear that we have here a set of huge challenges and opportunities to develop prototype applications and use cases for as well the quantum computing and the quantum annealing devices. So in our vision at the Jülich Supercomputing Center, to get the best out of these quantum computing devices is to link them with HPC systems. Why? First of all, we can use the HPC systems to perform simulations or emulations of the quantum computing and the quantum annealing devices. This helps us understanding how they operate. Maybe it also helps us in their design. We can see where they make failures and so on. And definitely they are of very much importance for benchmarking activities. But the final goal is when we link these two types of computing systems, the high performance computers and the quantum computers and annealers, then we can come to hybrid simulations for applications. So our goal is to combine the best of both worlds to come to use cases and prototype applications. So therefore, and I already mentioned this, I'm heading a quantum computer user facility, which is called UNIQ. And UNIQ stands for Jülich Unified Infrastructure for Quantum Computing. And this is a user facility built up at the Jülich Supercomputing Center. UNIQ is part of a quantum module, and the quantum module is one of the modules of the modular supercomputer architecture at the Jülich Supercomputing Center. In this modular architecture, we recognize a cluster which contains mainly CPUs. We also have there a module called Booster. This contains mostly GPUs, and then there are some other modules foreseen for storage systems, data analytics, and the more exotic computing systems like neuromorphic computing and quantum computing. Our goal is to come to quantum classical hybrid computing models by using this modular architecture. So a few words about UNIQ. As I said, it's a quantum computer user facility. It's for science and industry in Europe. It provides access to different quantum computing devices. And in order to do so, we install locally some of these quantum computing devices, we operate them, and we provide access to them. We do not only install and provide access to hardware, we also develop algorithms and prototype applications, and we know from our HPC experience that it's extremely important to also provide our users with services, training, and user support. And as I mentioned, our final goal is to come to modular quantum HPC hybrid computing by linking these quantum computing devices with our modular supercomputer at the Supercomputing Center. In UNIQ, we will provide access, as you can see from this picture here, to quantum computing devices with different levels of technological maturity. And one of them is a D-Wave quantum annealer. As I mentioned, we take a look at quantum algorithms and also try to develop some prototype use cases. So one of the things we did is looking at the quantum approximate optimization algorithm and benchmark it against quantum annealing. So QuIOA is a variational quantum algorithm. It's hybrid, so this means it uses both classical or conventional computing systems and a quantum computer. QuIOA relies on iteratively applying a series of parameterized unitary transformations with parameters or parameter vectors, beta and gamma, to a quantum register. Then one measures the resulting state and evaluates the energy expectation value. And usually one carries out a number of iterations that is larger or equal than 1. We use a classical optimization algorithm to optimize these parameters beta and gamma. And we know from theory that for P going to infinity, and if we choose beta and gamma according to a quantum annealing scheme, then the solution is found. But this is in theory. In practice, this is a little bit different because P will never be infinity. So we took as an application a two-sat problem, which is hard to solve with an annealer, with a quantum annealer. Why? It has one unique ground state, and this unique ground state is hidden from many first excited states. So we solved these two-sat problems with QuIOA, and in two different ways. So first, we made an emulation of a gate-based quantum computer on our conventional computer. And second, we used an IBM quantum computer from the IBM Quantum Experience to solve the same problems. And the two pictures at the bottom show you the difference. It's clear that the emulated Quaoa gives much better results than the one on the real device. Then we benchmarked this system with the D-Wave quantum annealer. And I'm a little bit afraid that I have this. Aha, there it is. So with the D-Wave quantum annealer, so at the bottom you see the success probability for 5 different problem instances. And what we compare is a D-Wave annealer. This was a 2002 system with an emulated Quaoa algorithm on a conventional machine. And from this, you see that in all cases, the D-Wave quantum annealer is performing better than the perfect, so to speak, Quaoa carried out on a conventional machine, but that, for example, for problem instance 4, you can see that the quantum annealer can also have a hard time to solve these difficult problems. Then a more real-world problem is a simplified tail assignment problem. This is a problem which comes from the airline industry. So here the goal is to assign aircraft to flights, and in the meantime, one has to minimize the overall cost for the aircraft and the flight crew while respecting the operational constraints. So, as an example, what an airline has to do is usually to operate and plan approximately 1,000 flights per day, and this to over 150 cities in over 70 countries using hundreds of aircraft of different types. And what we did here is we considered a smaller example of this simplified tail assignment problem. So we said we want to find two routes to carry out 472 flights. My clicker is not working properly. Okay, 472 flights between the airports. And the constraint is that the routes may not overlap. Now, this problem can be mapped to a quantum optimization problem with 40 qubits. So each qubit represents a root, and each root contains several of these 472 flights. So what we did is then we studied Quaoa, emulated on our conventional computer, one on our supercomputer, and this for the problem with 40 qubits. And then we evaluated how this Quaoa, this quantum approximate algorithm, performed. So what we did is we used the GPUs of our Jewels booster machine, which consists of QPUs, to do the quantum part. For the optimization, we used the CPUs of the Jewels booster system, and then we solved the optimization problem. Now you can see what we did here is we used 2 modules of the modular architecture. So here you can see the papers and also a small YouTube film if you are interested in this. So, but what I was saying that is we use 2 different modules of our modular supercomputer architecture. So we used CPUs for the optimization, GPUs for the quantum circuits. But what we also could do is we could use the CPUs of our cluster and a quantum processing units of the quantum module to do the same calculation. And then we can really speak about this integration of quantum and conventional computing units in this modular architecture. Now we emulated everything, but in principle we can carry out, of course, this quantum circuit part on a QPU. Then we used the same problems to solve them on a quantum annealer. First of all, I show you at the top the QuaOA results for you as a kind of reference. So you see that the success rate for the QuaOA and 40 qubits is less than 10 to the power -2. These are the dashed lines on the graph. Then we made a comparison between the D-Wave 2000 system and the D-Wave Advantage system for these 40 qubit problems, which are relatively small problems. And here you see results as a function of the relative chain strength, but you can see that Advantage can solve these problems with a success rate which is higher than 50%. Needless to say is that on Advantage, we also have carried out simulations for larger systems, namely up to 180 qubits. Then I want to go to other problem, which is quantum machine learning. So we have implemented the support vector machine for supervised machine learning for classification and regression on a quantum annealer. And this has some advantages. The reason is that the quantum annealer produces various close to optimal solutions for training data, whereby the different solutions often emphasize different features of the training data. And if you then combine these solutions to the test data, then your classification task might be better, might give better results with the quantum support vector machine than with the classical one. Here you see a simple example of this, where the classical support vector machine is used to classify 40 points into inner and outer points. And then you see that the quantum support vector machine gives different boundaries, classification boundaries. If you add then these three different results for the data, then you come to better results. We have applied this, and I have unfortunately to go a little bit faster here, to an application of computational biology, namely for protein DNA binding. The outcome was that the quantum support vector machine performs better or comparative to the classical support vector machine, and this for all data sets. We have used the same method. Clicker is again not moving forward. For classification of remote sensing, multispectral images for classification. And what we there did was we looked at a multispectral image of the city of Toulouse and made a comparison between the classical support vector machine and the results of the quantum support vector machine. From these images, but also from other results, you can see that the quantum support vector machine gives similar results or even better results than the classical support vector machine. Here, training sets were 100 samples with and without buildings, so 50 with buildings, 50 without buildings. And then I will skip the latter one, which was an example. Unfortunately, now the clicker moves forward. So this was just other machine learning application for the compression of convolutional neural networks with quantum clustering. And also here, we find similar results for the quantum as for the classical method. And with this final slide, I would like to conclude. So we think that the key to a successful development of quantum computing applications is really this linkage of high-performance computers and quantum computers and annealers, which is more or less already done with hybrid solvers of D-Wave. So thank you very much.